So good afternoon. We are surrounded by metallic circular hollow sections in the built environment. They're used as structural members in buildings and bridges, thanks to their aesthetics and their good range of structural properties. These tubes are typically formed from carbon steel, stainless steel, or aluminium. Stainless steel is becoming increasingly commonplace, with a greater emphasis on sustainability, thanks to its high strength, recyclability, and inherent corrosion resistance. Stainless steel circular hollow sections are therefore expected to become more prevalent in construction in the future. When designing these tubes, structural engineers use design standards which provide expressions for predicting the failure load. Design standards need to be efficient. You do not want to use an excessive amount of material to resist the applied load. However, they also need to be safe and efficient. Existing compressive data shows that the current European stainless steel design standard can predict unsafe capacities for certain lengths of circular tubes. The design standard may predict a failure load of 100 kilonewtons. However, if you were to squash this column in real life, it may actually fail at 80 kilonewtons. And this is clearly not good if you're designing bridges and buildings using this design standard. The reason for this mismatch is that design standards are based on the available structural data. And at the time the standard was developed, there was a very limited number of existing tests. And the existing tests were only carried out on one of the three types of stainless steel used. So the aim of my research project was to increase the amount of stainless steel circular hollow test data and then to develop more appropriate design guidelines. The first step was to undertake an extensive testing program covering all three types of stainless steel used in construction and a wide range of thick to thin-walled tubes with lengths varying from 20 centimetres all the way up to 3 metres. In total, 47 columns were tested to failure, both here at Imperial College and at UPC in Barcelona. This new experimental data has been supplemented with additional computer modelling. Finite element models have been developed that can closely replicate the experiments, and these have been used to produce additional structural data. Previously, there were only 29 results in the data set, and now there are over 530 results. With this new comprehensive data set, I've gone on to develop more appropriate design rules that can more accurately predict the failure load of stainless steel circular tubes. The outcome of this work is that structural engineers can continue to design and build iconic structures with hollow sections using design methods that are safe, efficient, and reliable. Thank you.